So hello everyone. Thanks for the organization of the workshop. So my name is Marco Fellous Asiani, and I will present to you these two things. Originally, I've been asked to present the IEEE Working Group, that is a working group to define energy efficiency for quantum computers. But there are many things we are currently discussing, so making a full presentation on this will be a little bit light. So this is why I've been suggested to at the same time present a scientific paper about minimizing the energy consumption of quantum computer and the link to the IEEE Working Group, because this scientific paper will also help you to understand how we can define energy standards. So I will begin by talking about this scientific paper, which explains how we can minimize the energy consumption of quantum computers. And at the same time, it will also be very instructive to understand how a quantum computer uses energy and how we can define an energy cost for a computation. So before talking about energy, I think it's good to go a step back and remember ourselves why we want to build a quantum computer. So we want to build a quantum computer because there are some mathematical problems we want to solve, and they are characterized by the size of the problem we want to solve. And there exists the best classical, for some tasks, the best classical algorithm we know can have a complexity in the number of operations that is exponential with the size of the mathematical problem we want to solve. While the best quantum algorithm that exists can have a complexity that is polynomial. So it means that if the problem we want to solve starts to be sufficiently big, then the quantum computer will require a lot less operation than the classical one, and then we expect that if the problem gets sufficiently big, the quantum computer will save a lot of time. But this is also clear that we will have energy gain with quantum computer for the same reason. If you have much less operation on a quantum computer at some point for a big enough problem, then the quantum computer will save energy compared to the classical one. But what is not clear is when this transition occurs between the moment the quantum computer saves energy compared to the classical computer, because this crossing could be very different from the crossing in computational time. It could occur at different places. And so the goal of this work is to find where it occurs and to put this transition where the quantum computer saves energy the earliest possible for the smallest problem size. So this is what it means to make an energy efficient quantum computer. It means making it save energy for the smallest problem size you can have. So in this work, this is essentially what we are doing. We provide an approach to make this occur. So then what we will do is, so I will explain how we do this, but then we will apply it in an idealistic model of quantum computer based on superconducting qubits. So I say idealistic because there are optimistic assumptions about the qubits quality. But the model is really complete, so that's also the first attempt to make a complete energetic model of quantum computer. And we will minimize the energy and power that are required to crack the encryption, to decrypt the RSA encryption algorithm, which is a way to protect data, to secure communication classically. So with this computer, we look at the energy it requires. And yes. But so what matters, in my opinion, here is more the approach rather than the quantitative estimate, because this quantitative estimate are, of course, rely on some assumptions. So I will first explain how we do it, the methodology, and you will see it's a quite natural way to formulate the problem. So the first element in this methodology is what we call this methodology is called metric noise resource, and the first element is what we call the metric. So the metric, it's one number that quantifies how accurate your computation is. So to put it simply, imagine the probability that your algorithm succeeds. That's the simplest example of metric. And what you want is your metric to be bigger than the target. You want your computer to succeed more often than a given probability, because otherwise it means it does not work. Then you have the noise. So the noise is a process that affect the qubit and that introduce error on them. And if you have a lot of noise, then naturally your metric will be poor. You have the resource, so the energy or the power, the thing we want to minimize. And on top of that, you have what I will call the computing architecture parameter. So this parameter can come from a very different field of science. It can come from computer science, like the way you compile the algorithm, down to physics, like the temperature of your qubit. And when you will modify this parameter, you will modify on the one hand the noise felt by the qubits, but also the energy that your computer requires. And because the noise will be modified, you will modify the quality of your computation, so the quantified by the metric. And what we do is something quite natural. We look at the different parameters in this architecture to find the ones that minimize the energy to perform the computation under the constraint that the metric is sufficiently big, bigger than a targeted metric we want. And by doing this, so we will make the computer energy efficient, but we will also be able to optimize its whole architecture. The thing that is non-trivial is to understand how this computing architecture parameters, so they will of course modify the energy, but also the noise felt by the qubit. And this is the thing you need to go down. And to do this, you need to go down really down to the physics of the quantum processor. So you need to understand why your qubits are noisy. So you need to understand the dynamics that your qubit face during the computation. It will tell you why they are noisy. And then you need to understand how this noise is related to the architecture. And by doing this, because you will have this connection between the noise and the architecture, you will be able to optimize the whole computer architecture based on the quantum physics of the quantum processor. And the interesting thing here is that at the end of the day, when you have that, so you have these control parameters, they characterize your whole computing architecture, and they can go from quantum hardware, error correction, algorithm. This parameter can affect all these elements. And you know that they modify on the one hand the noise, on the other hand the resource, and because they modify the noise, they modify the metric. And by solving this minimization under constraint, at the end of the day, you have one equation that summarizes your whole computer. And by solving it, you will be able to optimize your architecture by taking into account all the interdependencies between the field, which is something that is usually seen as challenging in the sense that usually we try to focus on hardware on the one side, on error correction on the other side, on cryogenic on the other side. Here we have a unique equation that mixes everything. So we can really find a global optimum. So this is why this is a holistic methodology. So yeah, the methodology is actually quite natural. So now what we need to do is to apply it to a complete model of quantum computer. So in this work, we developed a complete model of quantum computers. I will not go into details here. I will just give you an idea of the elements there is. So on this image, you see this gray box. It represents a cryogenics unit. And so basically your quantum computer, there are also things that are outside of this cryogenic unit that are in your computer. In some sense, we model them, but I would like to explain what there is here. That's the most important. So each gray plate that you see here is a cryogenic stage at a given temperature. And you have the top stage is the stage where we generate the signal that will drive the qubit. And the stage at the bottom is the stage where the qubits are. And there are inside of this figure, there are also the amplifier, you need cable. So all these things we have then in the model. And now, as I said, we need to specify the parameter we will play in during our optimization. So in this work, we choose to optimize the temperature of each of the gray stage. So actually, it's not exactly each of the gray stage. We do not optimize the temperature of the amplification stage. But to summarize it briefly, we optimize most of the temperature in this cryogenic unit. We optimize also one thing that is called the attenuation. I will come to it later. And we optimize the number of physical qubits per logical qubit. So what I mean by that is that we are doing error correction. So each logical qubit will be encoded with a given number of physical qubit per logical qubit. And so here again, what is very important to understand is that when you modify any of the parameters I say we optimize, we will on the one hand modify the consumption of the computer. Here we will minimize its power consumption, and from that we will deduce the energy. But so it modifies on the one hand the power consumption, but also the noise felt by the qubit. So it modifies it too. And as I said, we are doing quantum error correction. So let me explain a little bit. So when you do quantum error, so I will explain after why we chose the code we chose, but let me first briefly explain how it works. So when you do quantum error correction, you have a logical qubit that's the qubit that your ideal algorithm needs, but it faces error, and to face it, you encode it in a given number of physical per logical qubit. And there is a parameter, so here it's called K, the concatenation level, such that when you increase this K, you add physical qubit per logical qubit. So your computer gets bigger. And why do you want to do this? Because you can define a probability of error of a logical gate, so logical gate, but now with error correction, and it's a function of the probability of error of a physical gate, so a quantum gate if you did not do error correction. And basically, if this physical error probability is below a constant that is called the threshold, it depends on the code you use and its implementation, you see that when you increase this K, in this parenthesis here, you make the quantity goes to zero if you increase more K. So it means that you reduce your probability of error when you have each logical gate protected by error correction, but it has a cost. You have more physical qubit per logical qubit. But this is how it works. If the physical error probability is below the threshold, then by adding sufficiently many physical qubits, you can make converge to zero your logical error rate. So in this work, we used a specific code, which is called the 7-qubit code or the STIN code, and it's concatenated implementation. The reason why we use this code is that it allowed us to have a complete analytic model before doing the minimization. Then the minimization is done through numerics. But we wanted to have this to really understand very nicely how a quantum computer uses energy and all many trends, which would not be easy to do with a more, let's say, more state-of-the-art approach like other code, like the surface code, because it has better performance, but it's also, in some sense, it's also less understood. So we wanted to be sure we have a model that we understand nicely. So at this point, basically, you have all these parameters in code that you optimize, and you sit down. Okay, you can write down the power consumption of the computer. You have a big function, but you can write it down. So then, that's one thing, how the control parameters are related to the resource. So here, the power consumption. So now the other part of the problem is to understand how they affect the noise and then the metric. So for the noise, we consider a Lindblad equation, which is this kind of differential equation. Where the part in green is an operator that describes the noiseless evolution of your qubit. But your qubit will feel noise, and it's represented by this operator in red here. So you would like this red operator to be equal to 0. And here we consider, in some sense, the simplest noise model that superconducting qubit face. And in this noise model, you have different parameters. You have first this N noise here. So this N noise here represents the number of noisy photons that interact with your qubit. So if you have a lot of, because you send photon to drive your superconducting qubits, so if you have a lot of noisy photon you will not like to be there, then of course your evolution will be noisy. So in practice here, we focus on the thermal noise. So we assume that the only reason why the qubits are noisy is because of temperature. So if my qubit was exactly at 0 Kelvin, in an ideal world, it's not possible in practice, but as an idealization, this N noise would be equal to 0. But you can notice that even if N noise is equal to 0, this red operator will not vanish because of the coefficient gamma. So this is called the spontaneous emission rate, and it's a fundamental limit for the quality of your qubits. So it represents the fact that even if I was in an ideal world where my qubits were exactly at 0 Kelvin, they would still face noise because of this fundamental effect. And this coefficient gamma, in some sense, represents the intrinsic quality of the qubit. We want gamma to be the smallest possible, but then it's given by the hardware. So yeah.
Is this E in sigma minus sigma plus? What are these terms?
Okay. Yeah. So there is a question about what are these D and sigma. So to put it simply, they are called dissipator. These are operator. The D of sigma minus, it's an operator that tells you that your qubit, it will relax to the ground state and emit and this D of sigma plus, it will excite to the excited state. But you don't want it because it's noise. But sometimes this is what will occur, and this will introduce an error in the computation.
Yeah. Sorry, Gary. So
yes.
So I'm not an experimentalist, but is this the gamma related to thing that they call like the T1 time?
Yes, exactly. So you can so all these things basically all this gamma, so all this term here, gamma times N noise and gamma times 1 pi noise plus N noise, you can deduce the T1 and the T2 based on that. Basically, the T1 will be the inverse of gamma. Okay. I mean, proportional to the inverse of gamma. Yeah, and yes, so now there is a question of how do we relate this noise model to the architecture of the computer, because we need to understand how, when I will modify all the temperature, it will modify the success of my computation. So in our work is done through the N noise dependence. So basically, as I said, if my qubits were if my qubits are hot, they will feel more noise. So then it necessarily depends on the temperature of my qubit. But actually, it depends on more things. Because let's give an example. Imagine that you generate signal at room temperature and you directly drive your qubit. Then there is a lot of noise in your signal because maybe your qubit is very cold, but all the signal you send are very hot. So then it will introduce noise. So this is why actually the noise felt by the qubit is not just linked to the temperature of the qubit, it's linked to the temperature at which you generate the signal. So this is represented by this term here and here of T generation. But you can mitigate this by putting attenuation. So an attenuation, to put it simply, it's a big resistor, and basically it dissipates the signal at its input, so it dissipates heat in the computer, so it will increase the energy consumption of the computer because we need to remove this heat and it costs energy. But the interest of doing this is that it will also remove the noise coming from the hotter stage. So it's a kind of trade-off. You dissipate more heat, but you remove the noise at the same time. Okay, and so this is how the noise is related to the architecture. And so this attenuator, this pink thing that I showed on the graph, and as I said, yes, I will participate to the consumption because I will dissipate heat. And actually, I simplified a little bit the story. Technically, the noise felt by the qubit is a function of all the attenuation we put on every stage and the temperature of every stage in the cryogenics. So it's a more complicated formula, but it's essentially the same idea. But this is, in some sense, this is how we can also optimize the architecture. This is good that we understand this dependence because this is through this that we will optimize the architecture of the computer later. So now there is the last thing. So we understand the noise. And now that we understand the noise, we can deduce the probability of error at physical gates in the quantum computer. So it will be a function of the temperature and the attenuation. And from that, we can also then deduce the probability of error of a logical gate. So it will depend on the probability of error of a physical gate. And then because of that, on the temperature and attenuation. And also on this parameter K, which I recall is related to the number of physical qubits per logical qubit. And the metric we use, we say it's defined as the probability that no gate fail along the whole computer. And so it will depend on the probability of error of the logical gate. And so we have a function here on this parameter we control, and then we say we want the algorithm to succeed 2/3 of the time. That's an example. And that will constrain our control parameters.
To make it clear,
yes.
The algorithm succeeds means it's a valid result, not the desired result, because the algorithm gives the correct, let's say short, for example, gives only a correct factorization with a certain probability. So algorithm succeeds means we get a correct result from the algorithm, not our desired result. Correct?
Yes, yes. Yeah, I agree with you. That's indeed how it's defined here. We ask that no quantum gate fails along the computation with a given probability. Now it could be that if no quantum gate fails, because of the specificity of the algorithm we use, it still does not give the answer.
Yes.
Yes.
Okay, thanks.
Yeah. Yes. So that's the constraint we put. And then we are ready to apply this on a complete model of quantum computer and do the optimization. So here I would like to recall that's a toy model because they are simplifying an optimistic assumption. So for me, the most important assumption here is really the lifetime of the qubit we use. So it's related to the fact we use the code we use, which require very good qubit work. So to give an idea, the qubits are 2 to 3 orders of magnitude better than the state of the art. Yeah. There are other optimistic assumptions. I will not go into detail here, however, because they are, let's say, much less. The main optimistic assumption, in my opinion, is really the first one. The rest, they are a bit optimistic, but not at the same level. And one thing I would like to mention is that here for the efficiency of the cryogenics, so you know that if you want to remove heat inside the cryogenic unit, you need to provide energy, and there is the efficiency at which you do it is limited, and the optimal efficiency to do this is Carnot efficiency. And here we consider Carnot efficiency for the cryogenics, and it's actually a good assumption for large scale. Large scale cryogenics can be made quite close to Carnot. And final, so I will present the result in the next slide, but basically, they will be represented as a function of the number of logical qubits we have in the algorithm and the number of time steps we have in the algorithm. So this is the result of minimization we can have. So basically, on the x-axis here, there is a number of logical qubits we have in the computer. And on the y-axis, there is the number of time steps in the algorithm. So here we see, for instance, that to crack RSA 2000, which is the current level of encryption, with our model, it will cost 7 megawatts for a few hours. That's one quantitative estimate. I recall that each point here is a result of an optimization. So we are not doing an estimation. Really, the whole computer is optimized so that it minimizes the power consumption for each algorithm we implement. You can see there are brutal change of color here. This brutal change of color, they are related to the moment where we need to add physical qubit per logical qubit. So when you do this, the power consumption increases when you cross these transition lines here. So, okay, that's a quantitative estimate, but for me, this is not what is the most interesting. What is the most interesting is to understand how the computer uses energy. And to understand this, we can look at the qubits temperature. So here is the same graph, but now I represented the qubits temperature. And let's say I start from this blue point at the bottom here, and my qubits are 500 millikelvin. So to give you an idea, typical superconducting qubits are at 10 millikelvin. So this is very hot for superconducting qubits. So why are they that hot? Basically, because we are just after a transition where we added physical qubit per logical qubit. So then the simulation tells us, okay, you want your computation to succeed, but you want to minimize the energy to do it. So to do it, because you are doing a lot of error correction, put your qubit hot. There is no need to maintain them cool. You would spend too much energy if you did this. So put your qubit hot, it's fine because you're managing the errors with error correction. And then you increase the duration of the algorithm, so the depth here. And the temperature of the qubit decreases until it reaches 4 millikelvin. And here, during this decrease, there is a constant number of physical qubit or logical qubit until you reach this point here, where the simulation tells you, okay, if you want to implement an algorithm that is longer, it's possible, but now it starts to be quite long. So we need to fight noise more. So far, I could fight noise just by reducing the qubit temperature. But now, if you want to fight noise more, you need at this moment to add physical qubit per logical qubit, because only playing with the temperature, either it's not sufficient to fight the noise, either it will cost me too much energy. So here the script tells me, okay, the optimal strategy here is to add physical qubit per logical qubit. Then you do this, you pass the transition, and now you're doing a lot of error correction. So the script tells you, okay, now to minimize the consumption, put your qubit at a hot temperature. No need to maintain them cool, because you're doing more error correction now. Yes.
What is the time scale on the steps? Is that milliseconds, nanoseconds, seconds?
So the duration to implement a step depends on the number of physical qubit per logical qubit. So one step in this area here takes more time than one step here, but the difference is not so big actually. So to give you an idea, it's between 100 nanoseconds and 1 microsecond. And the exact value will depend on the area, but it gives you an idea.
So with microseconds, okay?
Yeah, you can consider it roughly microseconds for one time step. Yeah, so the graph on the right really explains how an energy-efficient quantum computer uses energy in some sense. And here, the thing that for me is interesting is that it is really a multidisciplinary behavior that we have here, because here we see that, so first the temperature, they are still quite cold. I mean, 500 millikelvin is hot for a superconducting qubit, but at the end of the day, it's very close to the zero absolute with respect to our scale. So this is because we use superconducting qubits, right? We see that it depends on the way we implement the algorithm, because when I make the algorithm longer, my temperature varies accordingly with the algorithm I am implementing. It depends on the error correction I've chosen, because this is what specifies me my boundary lines here. And it also depends, of course, of cryogenic and engineering. The reason why the script still tries to put the hottest temperature it can is because we want to minimize the power consumption, and the fact that Carnot efficiency plays a role there, for instance. And one thing I would like to mention here, which I will come back to it after, is that the power consumption per qubit adapts to the computation performed. So how can we see it from this graph? Basically, here on this line, we have 1,000 logical qubits. And when we are between those 2 points, the blue and the red point here, we have a fixed number of physical qubits per logical qubit. But the temperature varies. So it means that the power consumption of the computer varies because the temperature varies. And we have a fixed number of physical qubits in the computer. So it means that the power per physical qubit depends on the algorithm we are doing. So in some sense here, I will come back to it after, but an energy efficient quantum computer, this is how it should look like. The consumption per qubit is adapted to the algorithm we implement. Yeah. And now there is a question is, okay, we are doing optimization. How much can we save by doing this optimization? So I will not say it's the case in every plot. It's highly dependent on the regime you look at. And actually, this is for a slightly different parameter than the one I used before on the plot I wanted to show you for pedagogy. But in some of the plots we realize that without applying this holistic optimization, the consumption of the computer could be up to 10 nuclear reactors, while when we do the optimization, we can reduce it to a few megawatts. So it shows that it's not just, okay, optimizing like this, but it can really make the difference between an impossible and a possible architecture. And I think it's very interesting to understand how it's possible. So basically here, one reason behind this game is that in this case, the simulation finds it smarter to put the qubits hotter than what they are typically in superconducting qubits. So well, they will do more error, but you compensate by doing more error correction than what you will naively do. So you have a quantum computer that is bigger than expected, but it spends less energy to be maintained cold because there is, but it spends less energy to be maintained cold. So you have an energy gain. So here that's sorry. Yeah, sorry.
Could you move up the?
Yes.
No, because I don't.
Sorry, it's in.
Sorry. Yeah.
Yeah.
Maybe I can put it up. Maybe I can hide it. No.
No.
Hide floating. Yeah, I think. Oh.
Yes. Okay.
Sorry.
No.
Okay.
Yeah.
Sorry, because I couldn't see what was in the.
Sorry to interrupt.
Yeah, no problem. Okay.
Yes.
Okay, so I will really explain this. So basically, one reason behind this gain is that the simulation finds it smarter to put the qubits hotter than what they are typically in superconducting qubits. So they are doing more errors, but we compensate by doing more error correction than what we typically do in a quantum computer. So you have a quantum computer that is bigger, but that actually is more energy efficient because the qubits are hotter, so you need to spend less energy to maintain them cool. And here the holistic aspect is quite clear because when you start touching the qubit temperature, you modify the energy spent by the cryogenics, but you also modify the noise felt by the qubit. Because the noise felt by the qubit has been modified, you have to modify the quantity of error correction you need to do. And the quantity of error correction you need to do depends on the algorithm you want to implement. So here it really shows that in some cases it's very interesting to link all the interdependencies because it can make the difference between a possible quantum computer and one architecture that might be implausible to make. In the paper, we also observed a regime of energy advantage for computation that are classically solvable. So it means that a classical computer could solve the task in a reasonable time, but our quantum computer spends less energy to do it than the classical computer. So again, this is based on our toy model. So I'm not saying that it's a proof that it will necessarily occur, but I think in some sense we choose a very poor error correction code that has very bad performance And the fact we observe it with our code for me is very interesting because it means that with more powerful error correction method, this conclusion could possibly be reinforced in some sense. Okay, so I've also been suggested to insist a little bit more, or maybe effects that are not completely intuitive on how the energy is used in quantum computers. So I will comment a little bit on this. And after we'll talk about the IEEE Working Group. So basically, I recall that, okay, what we do is we minimize the energy under the constraint that the metric of success is greater than the target. And one thing to realize is that first the power, so I said it a little bit before, but then it means that the power per qubit will depend on the algorithm we want to do. It's not a constant. So let me explain what I mean. And when I mean by per qubit, it's true either for the logical qubit or the physical qubit. Yes?
Question to that. Not only depending on the algorithm, but also depending on the architecture where you execute it. There are cases where it is useful to extend to ancillary qubits. Is that something you can take into respect or not? Because right now I think you're not taking it.
So yeah, I agree with you. So of course the power per qubit depends on many things in general. But here what I want to say is that the quantum computer has a fixed type of qubit. It has fixed choice of error correction. The only thing I change here, for instance, is the success I want for my algorithm. And I do not change any other thing. I just say I want my answer to be 90% accurate, 99% accurate, this kind of thing. So in this case, the point I want to raise is that the consumption per qubit, that they are either logical or physical qubits, and the implementation of the algorithm is identical. It's just that I vary the success I want to it, will depend on the success of the task. And so for the number of logical qubits, let me give an intuition. So here, imagine that you want to run an algorithm that has 70% success probability. You will need a given number of physical qubit per logical qubit. But imagine now that you want your algorithm to be successful 99.99999% of the time. You need to do more error correction because you want a super trustable answer. So that's an example where the size of your logical qubit, so the number of physical components it is composed of, will depend on the target success. But so this is a bit expected, but for me, what is more interesting is that it also depends, even if you fix the amount of error correction, the power spent per physical qubit will depend on the targeted success, because fix the amount of error correction, ask an algorithm to be more accurate, will, for instance, cool down more your qubit. And so then the power consumption per qubit will depend on the success. And what it means is that basically, if someone tells you I have a quantum computer that has this number of qubits, how much energy it consumes, without more context, it's not possible to answer the question. You need to ask the person how accurate you want your computer to be. If you give a number that is independent on the success of the task, it either means that your computer will just not give you an answer that is trustable with what you would like to have, or that your computer is not energy efficient. You spend too much energy, you could spend less energy to do it. A very related thing is that, so imagine that I run an algorithm. Let's say I pick an algorithm and I increase its duration by, to put it simply, I just run the set of gates 10 times, let's say. And I vary the duration of my algorithm like this. So we might expect at first view that if my algorithm is 10 times longer, I consume 10 times more the energy because it's just 10 times longer. But actually, it will consume, if the computer works with the success you want and is energy efficient, it will spend more than 10 times the energy. Why? Because your algorithm is 10 times longer. So of course you have to spend more energy for that. But you need to preserve information for a longer time as well. And this has an extra cost that you need to provide. So basically, you should imagine that the energy spent grows quicker than linearly with the time of the algorithm. And this is what an energy efficient quantum computer that works with the success you want to work look like. Okay, and now I will talk about the IEEE Working Group. So you will see that some of the things I presented here, they are related to how to define this. So the goal of the working group is to define a platform-agnostic way to quantify the energy efficiency of a quantum computer. So we want that if someone comes with an ion trap quantum computer or a superconducting quantum computer, even though the technology are completely different, we can say your quantum computer is more energy efficient than his. So The thing, so, and I would like to insist on the fact that everything I say here is really under discussion. So maybe some of the things I say here will change, and maybe, yeah, but to give an idea of the question. So we are thinking that basically we should define an energy. So for a task, such that it succeeds with a targeted metric. Because as I said before, it's completely meaningless. If you do not specify the accuracy of the computation, you cannot infer an energy cost. So yeah, that's how it will look like. And then basically, it means that the quantum computer can run different tasks. And it means that the standard will not be a number, the energy to run a task, but rather a curve. The energy to run a task as a function of the quality of the answer you want. And this is what every architecture should compute. Now the natural question are, which task should we look at? There are many tasks, many computational tasks. So here, what we are currently thinking, but again, it's under discussion, is to, so first there are different types of tasks. We can think about high-level algorithm. So for instance, you want to implement, I don't know, short algorithm, or you can also think at a gate. Like my task is just, I want to do a CNOT or a swap. So here we focus on high-level tasks. So the thing we are currently thinking of is, because there are infinitely many algorithms we can do, is to look at the important subroutines and to say that people should do the curve I showed before for all the important subroutines in quantum algorithm. So that if you combine them, then you can deduce the energy for any task. Then there is also a question, which is, how do you quantify the success? Because when I talked before, I told about the probability that the algorithm succeeds. The thing is that it's not always possible to quantify it. Sometimes it's not even possible to compute this probability. Because to put it simply, in some sense, if you were able to exactly compute it for any algorithm, it's not, what I say is not exactly true, but it somehow means that you know the answer of your quantum computer beforehand, but you don't know the answer. So it's not completely true what I say here, but it's just to give an intuition why in some cases it can be complicated. And so then there are many choices of ways to quantify the success of a computational task, which are advantage and drawback. And here we would like to avoid going in this debate because that's a scientific question in itself. So we just want to say that our standards should work for any way we quantify the success of a task. So we just make sure that, yeah, okay, you quantify the success this way, then the definition of our standard makes it easy to compute it, is the way we define it. And let me give an example of how it could be used. So imagine you have an algorithm which has, you want it to have a success probability 70%. And your algorithm is decomposed as subroutines. So, primitive tasks, and by combining them, you implement the algorithm you want to do. And to reach 70% of success for this task, it means that each of the subroutines, you can compute it, should reach a success 90%. And then the whole task will have 70% of probability. And so then, if our standard is well defined in the sense that you have quantified the energy to implement each subroutine, you will have a graph per subroutine, the energy as a function of the target. And then you will look, okay, for this subroutine 1 to reach 90% of success, it costs me this energy, for this one, this energy, for this one, this energy. And by summing the energy of each task, then you can deduce the energy of any algorithm. So in some sense, and that's one of the, again, that's really in discussion, so I don't want to say that's necessarily where it will go, but that's one of the things we discussed, that yeah, if we have done our job properly of looking at all important tasks, and then each platform can compute this curve, and then from that they could deduce the energy for an arbitrary algorithm. And the interesting thing is that it's completely platform agnostic. I do not need to specify assumption about the technology. Each platform can compute these curves. So yeah, so the working group is accessible on this website. So the chair is Alexia Ofer, the vice chair is Dash Liu, and I'm the secretary of the working group. So that's it. So very briefly, so for the scientific paper, for me, the main message is this kind of holistic approach. By doing this, you can make interesting optimization to minimize the energy consumption of the computer, because you see it as a unique physical system. And yeah, we are currently discussing some of the things in this working group. So yeah, thank you. And so here in the red box, that's all the people that participated in the paper I presented. So Robert just presented it before, actually. And I would like also to thank all the people on the left column here that helped us a lot to build the model. So thank you.
I have two questions actually. So the first one is your metric. Does it take the actual parameters also as an argument?
Yes. So it's indeed. So the metric will depend on the parameter we control through the noise. Basically, the noise is a.
But the noise could lose some information about the parameters, right?
What do you mean by the noise could lose information?
Like suppose I have 10 parameters and the noise only is a function of 3 parameters.
Yeah, it can be, but it's
so
not.
I'll be losing information when I define the metric.
It's not a problem. It just means so. Your parameter will modify on the one hand the power or the energy, on the other hand the noise. So it could be so. First, I will call them parameter if they impact either the resource, either the noise, or both. If they do not impact, there is no point in tuning them with respect to energy. So then it could be that your parameter only impacts the energy but not the noise. But it's not a problem because it will still play a role in the minimization under constraints.
Okay.
Yeah.
So that means you're fixing an algorithm for every metric.
What do you mean fixing an algorithm for every metric?
In the sense like you have an expected output and everything because the metric doesn't see all the parameters but only sees the noise it generates. It can't actually know the algorithm being implemented unless it is uniquely defined by the algorithm. Like the algorithm itself could be a parameter, right?
Yes, the algorithm could be a parameter, and then
the noise could not depend explicitly on the algorithm itself, but rather like other things, like the number of gates and things.
Yes, so I think your question means how are you sure that your problem is correctly parameterized?
Yes.
So indeed, that's part of the modeling. You need to the control parameter you have. You need to understand how, if you tune them, they will modify the noise and the resource. And it's not if it's not bijective in some sense, it might mean that it's not an appropriate parameter.
Okay. 1 second. And the second question is that did you consider running the algorithm multiple times to reach a success probability in the optimization?
Yes. So I will rephrase and you tell me if I understood correctly. You mean that sometimes it could be that reaching a success 90% on one shot is cost too much, but it's better to have 50% and you rerun the algorithm. So we did not do this in this work, but that's indeed a thing that should be taken into account if you want to. But it can be, just an extra layer of modeling. There is no conceptual problem.
Yeah, but the optimization problem could become a lot harder then.
Yes, I would say you might have one extra parameter in your optimization. So I think there are different questions. First, is the problem well defined? So for me there is no problem of here. There is no conceptual problem, and then there is the optimization costly to do?
Yeah.
So then your question is more about this. So here, for instance, the simulation, we optimized 4 parameters. I can explain why I say 4 after, but basically by optimizing only 4 parameters, we could make huge reduction, like the 10 nuclear reactor to a few megawatt, and it runs on a laptop on a few hours. So of course, the more you want to optimize, the more it will be costly, but already with a few parameters, you can do powerful optimization. So.
On the slide, it shows that the error code you choose has a duration time of 50 microseconds. How do you estimate that?
Millisecond. Yeah.
Milliseconds.
So this is what we consider in the model, and it's parameterized by this coefficient gamma here. So someone asked me the question about the T1 and the T2 before. So basically, the inverse of gamma gives the typical duration over which you can preserve information. So it's a typical time scale. And here, when I say 50 milliseconds, it means that 1 over gamma in the simulation is 50 milliseconds. Knowing that today, the state of the art, it's close to the millisecond. The thing is that there are different ways to quantify the quality of the qubit. So if you only focus on the lifetime of the information, the thing I showed is between 1 and 2 orders of magnitude better than the state of the art. But you, okay, so I don't know if it's, yeah, does it answer your question?
Yes, it raises my next question. Why is
Okay.
the units of gamma 1 over time?
This
Since
is,
this a continuous emission rate,
yes,
it shouldn't be a frequency, right?
it's a rate, so it's events per unit time. Here you can see it, you have row dot here.
Yeah.
So then this thing should have the dimension of the inverse of the time.
Okay.
And yeah.
Thank
I want to ask, like this whole model of this whole quantum computer with the error correcting code, like how much is it in a way modular? So like, let's say if I say, okay, I want to do this whole thing, but with a different error correcting code, could I just go through the paper and just plug in my values?
Yes and no. So the simulation script that we use to do this is very modular in the sense that if you change the error correction code, it's just a few lines to modify. Because I will slightly exaggerate, but more or less it's just modifying this equation in the simulation. So it's now we are doing trick to boost the speed of the simulation, which might make it a little bit less modular, but it's more practical. Like in this kind of thing, you can make it very modular. You model every part independently, and just at the end, you do the minimization under constraints. So that if you update a part, you just modify a local thing. Okay.
You can stay on this slide, but in general, on the NMR sort of methodology, you can say that for a second.
Okay.
Sorry, I was just going to say that you have obviously the control parameters as well, what you can control. In general, are all of those kind of the less energy you use, the worse sort of the worse the noise is going to get?
The more energy you use, the less noise. Yes, I agree.
Okay, and I guess compilation would be the only one that I wasn't sure on for that, I guess.
So actually there is a kind of a funny property that you can show, which is that imagine you have 1 billion of parameters you want to optimize, and there is just one parameter such that when you increase it, you reduce the metric and you also reduce the consumption. So let me give an example of a parameter that is like this, the temperature of the qubit. If you increase the temperature of the qubit, you will reduce the metric, your computation success will be worse, but you will also reduce the consumption. So if you just have one parameter like this in billion of parameter, then necessarily the bigger the success you want to have, the more energy you have to spend. And so I'm not, does it answer your question? I think, but I'm not sure.
I think for the other control parameters, that definitely makes sense. I was just wondering about the compilation, if that's also the case, that if you, does the energy consumption of compilation come into it kind of thing? Like if you reduce, I don't really know that part, how does that affect then? Because it definitely for the others, it makes sense to me that, you know, if you increase the operating temperature,
yes,
and that same relation holds, but I'm not
So
sure.
I guess for the compilation, it might mean what you exactly mean in the sense that there are two things I could call compilation. There is a classical computer that before the quantum computer runs, find the best circuit, and there is an energy cost to that.
Yeah.
And there is the fact that for a given algorithm I can implement on different circuits. And by changing the circuit, then it will modify the energy consumption. So are you talking about the first or the second thing?
So it has to be more like pre and post processing?
Yes. Pre-processing are a different way to run the same algorithm. Mm-hmm. So are you thinking about the energy to pre-process, which is a classical computer that does the job? Or are you talking about the different consumption we could have if we run different circuits that implement the same task? This one. So then how by changing the different circuits we run, it will modify the energy consumption. It's highly dependent on how it's parameterized. It's not possible to give because temperature it's like just one parameter, and we know it just move up or move down. But compilation, it's a multifactorial thing. It's not, so in that case, it's highly dependent on how you parameterize the problem of compilation.
Interesting.
Mm-hmm.
But you can come up with lower bounds, right?
So lower bounds on the consumption, you mean?
Yeah, because we can give lower bounds the number of gates required for algorithms and then use that for, so irrespective of how you arrange it, like you will still be consuming this much.
So that's so I guess it depends on the level of details you go in. If you, so to put it simply, if let's say each gate, let me try to give a clear answer. Imagine that each gate you want to do requires the same resources than every other, which is an assumption because it's not necessarily the case, but let's assume it's the case. And let's assume you have the same number of logical qubits to run your algorithm. Then if you increase or reduce the number of gates, it will just increase or reduce the duration. And in that case, I agree with you that the shortest your algorithm will be, so the less gate in this context, the less energy it will consume. But you can end up in case where it's not so trivial, because if some gates cost more than other, it's not because you have less gate than, yeah. And actually, not all gates have the same cost. Like there are what we call magic gates. They require specific protocols, and they are often seen as more costly than non-magic gates, to put it simply. But yeah.
I also just wanted to ask on the sort of error probabilities. So in general, it seems, you reduce maybe how much energy you're taking, but make the noise worse, but you could correct with it, so with your error correction code by adding more qubits. And I'm just wondering exactly, like, could you sort of recap what that threshold is and like how, because obviously adding more qubits takes more power itself. And I'm just wondering if you know that then at some point you might not even know where your qubits are, say if you keep increasing the operating temperature. And so I'm wondering what exactly is the threshold and how does that change for different error correction codes as well? So
so if I understand your question, you mean that, as I said, you can play with either error correction or temperature to minimize your consumption. And you're asked in which case it's better to do more error correction, but because it allows to put your qubit at a hotter temperature, or it's better to keep your qubit cold and do less error correction.
Exactly.
This is I cannot give a general answer. I'm wondering if actually one who gives kind of, that's something I'm interested in actually, to try to give some kind of generic models for that. Because it could be that, because for instance, the temperature, how to say, the noise dependence of your qubit often follows an exponential law with temperature, with the Boltzmann coefficient. And the logical error rate of an error correction code, it always have the same shape. So basically this is called the distance of the code, the 2 to the k. And my point is that there are, right now, I don't know the answer to your question, but it might be possible to derive simple model, maybe, where we can see kind of trade-off like this analytically. Yeah.
I have a question. If you're observing the circuits, then you see you have qubits that need more fidelity because they have a lot more gates applied to them than others. Could you, in principle, also generate a heuristic for that case? So, because right now, if you're looking at your slides, you're generalizing every qubit has the same
error probability.
Yeah, error probability that is needed. But for example, if you have just ancillary qubits for the algorithm, not for the encoding, then these have a lot less priority you need, and they could be at a much higher temperature than the others.
Yes, so I agree with you. That's a nice point. The thing is, so conceptually, I totally agree. In practice, it's complicated. Because in practice, when you do error correction, this physical error probability, actually, you never know, you don't know the actual error probability of your gate. What you know is an upper bound. And this upper bound is made by taking the noisiest gate, or the noisiest qubit, to put it simply. So then I agree with you that conceptually it depends on the probability of all different gates or different qubits, to put it simply. But then the formula are not known because it's too complicated. So yeah, but if one finds a nice model where he can, for specific qubit, know if I modify, if to know a function that is more tight and have different input, then we can do what you say, yes.
Yeah, because I could imagine you could basically do for a given algorithm classify your qubits in high duty qubits and low duty qubits.
Yeah.
But that would be maybe a possibility to refine your estimations.
Yes, that's true. That's true. I mean, there are definitely many things that can be improved and optimized better. It's a matter of how much work you want to do with the model. But yes.
And then you had this nice figure of the different stages of the cryostat.
Yes.
I'm not sure in the room how sort of familiar everyone is with the cryogenics. I'm definitely less, but I would just be interested for yourself. How much difference you think it makes for the different operating temperatures of the different hardware platforms? That if one needs 10 millikelvins and one needs 1 Kelvin, is this just like no competition now between the two stages, or what kind of other trade-offs will there be?
So you mean how sensitive to the temperature is the consumption so that we can reduce different patterns? So
as follow-up question then also would be that you sort of said we can correct for a lot of the noise by adding more physical qubits.
Yeah.
Do we know how for the different cooling stages how many qubits we can add, kind of thing? And were you just sort of taking the limit just as like infinite for your own simulations here?
So here indeed we don't assume we have a limit to the number of qubits because there is no. I mean, technically, you can put 1,000 billion qubits. Your cryostat might be bigger, but there is no conceptual problem. So your question is how sensitive the consumption is if I vary different temperatures. So actually, there is something funny that we found here. So you remember I presented two kinds of plots. The first one, a color plot at the beginning, where I explained how the consumption is used. And then I talked about this example of reduction from 10 nuclear reactor to a few megawatt. So the first example assumes a Carnot efficiency. And in this case, we observed in our model that actually, if you change the qubit temperature, you do not modify a lot the consumption of the computer because the consumption is dominated by things that are at room temperature. This was very surprising to us, because we often hear that superconducting qubits might consume a lot of energy because they have a cryogenics. But with the Carnot efficiency, we realize it's not the case, at least for the model we consider. You could imagine other architecture, of course, but then if you change for Carnot efficiency, which in principle is reachable, and when I say in principle, I'm not saying theoretically, I mean the Large Hadron Collider in Geneva, it works at a fraction of the Carnot efficiency. So it's possible, but it might cost a lot and be a very big infrastructure. This, I don't know the details. But if you take a cryogenic efficiency that is closer to what experimentally used today, then you need really to optimize the qubit temperature. And this is how we could reduce from 10 nuclear reactor to a few megawatts. So then if you compare different technology, my point, the big conclusion I would say is that it's not because the technology does not need cryostat that it will be energy efficient. Because in our, that it would consume less energy than a technology that uses cryostat, because it could be that the consumption of cryostat is actually negligible.
Very interesting. Yes. One final question on that would just be, how were you seeing the scaling between the energy consumption of the cryostat and the number of qubits?
So the thing here is that I don't think it's good to think in scaling as a function of the number of qubits. For me, it's the scaling as a function of, let's say, the size of the algorithm you want to implement and the success you want for this algorithm. Because as I showed example here, when sometimes putting more qubits is better because you're more energy efficient. Yes, and so now maybe you could come out by doing some trick to an argument with as a function of the number of qubits, but then in this case I don't know exactly. I think it's complicated because things are coupled. But yeah, I would suggest to think really about as a function of the number of gates, let's say number of logical qubit your algorithm needs, the number of gates it needs, and the accuracy you want. That's the three important parameters. And then studying how the energy varies as a function of these three parameters, for me, it's how we should phrase the problem. Yeah. Because when I say qubit in the algorithm, I say logical qubit, so which is not the number of qubits we need to put. So this is why it's not exactly the same as.
Could you imagine some scenario in the future where you would only cool to say 30 millikelvin and then use something like algorithmic cooling to go next or 20 millikelvin, and also
What is algorithmic cooling actually?
more for initial state preparation, but exactly that you can kind of like take the temperature of the qubits down.
Okay, it's like a trick to.
Exactly. Yeah.
Yes. I guess it's probably a trade-off as well, because I guess it might cost something to do this.
Exactly.
And there, it's a trade-off you could analyze in principle.
Interesting. And I guess actually maybe one final question about the IEEE Working Group.
Yes.
Just sort of more on it, sort of the questions that you're facing at the moment, and sort of how you see maybe, like, as you said, the error or how you determine it. Would you imagine that more the person, the user, makes their own decision on the trade-off, saying, I could take sort of less energy consumption if it meant less accuracy?
So indeed, this is so for me, let's say the point of the standard is not to tell people how they should optimize. It's just to objectively benchmark. Like I have a how can I say that some person claim he has a very energy efficient quantum computer better than another platform? We want to have a clear criteria to say if that's true or not. To make a kind of, for instance, a ranking of energy efficiency of quantum computers. So then the thing is that to compare, people will need to compare the same thing. So they will need, if I retake the slides here, sorry. It means that then, let's say I take a task, I don't know, a quantum Fourier transform on a given number of logical qubits, and just that the people should take the same task, the same target accuracy, and then they could compare, is my quantum computer to solve this task with this accuracy better than yours? And in some sense, it's not the property of the computer, but the algorithm that implement the computer. And I think it's not possible to go beyond that. And actually, it's also the case in classical computing. I think they run benchmark algorithms. So the energy efficiency is not a property of the computer, but of the algorithm that the computer implements. Yes.
And then a final question on the landscape. So I think just from your perspective, how many quantum computing companies or labs know kind of just at a very high level how much energy they're taking or the power consumption, and then how many people you know that are actually using this sort of framework or have more in-depth simulation? And I think even yourself, you haven't gone as far as you could go with these simulations.
Yes. So I know that at IBM, they looked at the energy consumption they will have if they scale up the way they do, and they quickly reached to a nuclear reactor, so they were scared. But the thing is that there are many things that can be optimized. Indeed, if you just blindly scale, it costs a lot, but people never try to optimize this. And so this is why there is huge gain that can be done if we just ask to optimize. So I know that at IBM, they looked into this, and I also know that at least in France, some startups look into this, like Alice and Bob, Candela, this kind of thing. But it's I would say, just starting. It's not like... because the problem with energy is that, for instance, if you want to count the number of qubits, you just need to think about the quality of your qubit, which is a constant, not a variable, like here, because here we play with parameter, and an error correction code and an algorithm. If you want to talk about energy, you need to add cryogenics, you need to add electronics. So it's also heavier in terms of modeling, which I think is also why it requires to invest more time to model this. But people are starting looking into this.
Any other questions from the room? Amazing. I think we'll have more discussions on
Yes,
everything that came
thanks.
up and especially the benchmark, but thank you so much. for
Yeah,
this talk.
thank you.
It's really informative.
Thank you.
Thank you.